Hello everyone. Today we are going to see new unit, that is unit number 7, and that is governor. All of you know that when Watt has developed his steam engine, at that time various mechanisms has been developed. Out of that, this governor is one of the mechanism which is used to regulate the mean speed of engine. Now when speed is varying, that is because of the increase in load, the speed will get decreased, and it is necessary to increase the fuel supply to that engine, or it may be considered as a working fluid. It may be fuel or it may be steam in case of steam engines. Nowadays we are not using steam engine, that's why we can say the fuel which is supplied to the internal combustion engine, that has to be increased. On the other hand, when the load on the engine get decreases, at that time its speed get increases, and thus less working fluid has to be supplied. Now governor do all this activity automatically, and that is by means of mechanical linkage only. That is, the communication is done by means of mechanical way, and the sense of that increase in load or decrease in load is sensed by means of these mechanical linkages, and according to that the working fluid has been increased or decreased. Now all these things are happen when the engine is in working condition. At that time, throughout its working, it may be the case that suddenly sometimes load may get increased or load may get decreased, and that is again depend upon the external application for which the engine is used. Now when we are going to see these governors, there are basically two types of governors. One is called as centrifugal type governor, in which centrifugal force is used as a regulating unit, whereas second type is inertia governor. Now for our case we are going to see centrifugal governors only. Now next part which we are going to see is the classification of these governors. Now these centrifugal governors are classified following. That is one, pendulum type, in which Watt governor is used. Watt has developed his governor for his steam engine which he has developed. And second type is called as load type. Now, as per the application, when the Watt has developed his governor, it was having some limitations, and to overcome that all limitations, another scientist, they have developed their own governors, and that are coming under the category of this load type governor, or external load is used, weight is used in that governors. That's why they are called as loaded governors, in which one type is dead weight type governors. That is, dead weight is placed, and hence it is called as dead weight governor. Or another case, it is spring controlled governors. Now in case of dead weight governor, there are Porter governor, Pronell governor, and in Porter governor also there are different types. All these types are coming under the category of loaded governors. Now according to the name of that developer, the governors are named. That is Hartnell governor, then Hartung governor, then Wilson and Hartnell governor, then Pickering governors. Now out of this we are going to see first of all very simple type of governor, that is Watt governor. Watt has developed his governor in 18th century. Now these are actual pictures of that governor, which are working on the principle of centrifugal force. You can see here the governor which has been used actually in engine in 18th century, that is 1788. Now this picture shows governor only with the engine. Now this is the schematic diagram of centrifugal type governor. In this case you can see there are two arms. At the end of the two arms, two balls are placed. That balls are having some mass, and they are connected to the engine shaft. So when that engine is going to run, that shaft is going to rotate. At that time these arms are also going to rotate. Now these arms where the balls are connected, they will start to rotate. And as you know that the centrifugal force, that is m r omega square, that will act on that fly balls. Hence what will happen, that centrifugal force will act in outward direction, whereas the inward direction, that sleeve which has been connected to that arms, that will apply his weight. and the sleeve will get move in upward direction or in downward direction, that is depend upon the centrifugal force. Hence this centrifugal force, as it is governed by means of speed, and that centrifugal force is going to govern the displacement of that sleeve, and that displacement of sleeve is directly given to the fuel supply. As the centrifugal force get increased, that is nothing but the speed is going to get increased, and hence the fuel supply will get reduced. Whereas if the centrifugal force get reduced, that is the speed will get reduced and sleeve will get displaced in downward direction, that arms will come inside, and hence what will happen, that fuel supply to the engine that will get increased. By this way, automatically the fuel supply to the engine that will be governed by means of this type of governors. Now all other terms which are there in this governor, that we are going to see later on. And here again the schematic diagram you can show, you can see that when the load on that engine get increased, the speed will get decreased. If the speed get decreased, then the centrifugal force will get decreased, and hence the centrifugal force will decreased, and what will happen, that ply ball will come inside, and hence the sleeve will get down, and as the sleeve get down, that fuel supply for that engine will get increased. As we are going to supply more fuel, hence the engine will run with more speed. It may happens that when the fuel supply is increased, engine speed may get increased, and when the fuel supply is decreased, engine speed will get decreased. And likewise we are going to get the control on the speed of that engine. Now this is the schematic diagram of the centrifugal type governor, which has been actually used in VAT engine. Now this is the VAT governor. Now here the schematic diagram has been drawn for the VAT governor, and this is very simplest type of centrifugal type governor. And when we are going to see a governor which has been used in the engine, when this VAT governor is considered, at that time there might be three possibilities. That is, when we are going to have arms, that arms may be interact with each other at the spindle. That is, you are going to see the point P in diagram number 1, that is A diagram. Whereas in case of B diagram, actually the P point is not on the spindle, but we are going to have one O point, where we are going to have the cross section of that arms, or that arms are going to cross to each other, and there is some offset in between that point P and O. But while we are going to consider for the calculation the H of that governor, that H is considered at the point O. This point P is very important while we are calculating height of that governor, and this height of governor is important while we are going to assess the sensitivity of governor, because this governor should be sensitive for change in speed. Now next we are going to see some terms which are used in governor. Out of that, first is height of governor. It is the vertical distance from the center of ball to the point where the axis of arms, that is arm that which are on which the balls are connected, are intersecting on the spindle axis. This is very important, that is on the spindle axis. The previous diagram which we have seen, in that diagram every time that arms are not going to have or in direct intersection on the spindle axis, but we have to extend it, or there may be extended part of that arm, but we have to consider the point where that arms are intersecting on the spindle axis. It is usually denoted by H. Then next is equilibrium speed. It is the speed at which the governor balls, arms, etc., that is all parts of that governor, all moving parts of that governor rather we can say, are in complete equilibrium, and the sleeve does not tend to move in upward direction or in downward direction. Now how the sleeve will move? Because of the centrifugal force, and if the centrifugal force is not changing, then the sleeve will not get displaced. Hence we can say that governor is in equilibrium condition. Now in this equilibrium, though the governor is going to rotate, it is called as dynamic equilibrium because that governor is in motion and hence it is in dynamic condition. And that's why the equilibrium which we are going to achieve, that is centrifugal force and sleeve weight, that equilibrium, that is called as dynamic equilibrium. Simply we can say the speed at which all these things are in equilibrium condition, that is equilibrium speed. Then mean equilibrium speed, it is the speed at the mean position of balls or the sleeve. Now how we can say mean position? There may be maximum radius at which the balls are rotating, that is they are flying out, and that will be the maximum position of that flying, whereas there may be minimum below which that balls may not come inside, and that will be the minimum position, that is called as the minimum position. Whereas if you are going to see the sleeve displacement, sleeve is moving in upward and downward direction, so there are limitations for the motion of the sleeve in downward direction and motion of that sleeve in upward direction. So out of that, if the sleeve is at mean, that is at the center, whereas that balls will be also rotating at the center, that is called as mean equilibrium speed. Next definition is of maximum and minimum equilibrium speed. The speed at the maximum and minimum radius of rotation of balls, that is balls are flying out, that is the maximum radius of rotation, whereas balls are moving inside, and limitations will be there for the coming of that ball inside, that will be the minimum position. And the speed at which these conditions are achieved, that are called as maximum and minimum condition, without tending to move either way, are known as a maximum and minimum equilibrium speed. Now these definitions are very important because in exam these definitions may be asked. Now next definition is of sleeve lift. It is the vertical distance which the sleeve travels due to the change in equilibrium speed, that is from lowermost position to uppermost position when the sleeve is moving, that is called as sleeve displacement. Now next in this slide we are going to see how to calculate the relation between speed and the height of that governor. Now you can say when this governor is in working condition and if the sleeve is moving in upward direction, at that time definitely there will be change in the height of that governor, which is denoted by h, because when the balls are moving outside, at that time what will happen, this h will get reduced, whereas when the balls are coming inside, this h will get increased. Definitely there will be limitations for the h, how much h can be reduced and how much h can be increased. Now let us consider that small m is the mass of ball in kg, w, that will be the weight of that balls in Newton, that can be calculated as m into g. T is the tension in the arm, because of the centrifugal force definitely tension will be generated in that arm, so that is denoted by T. Omega is the angular velocity of the arm and ball about the spindle axis in radian per second, the speed at which the balls are rotating, that is denoted by omega. Then small r is the radius of path of rotation of the ball, that is denoted from the spindle axis. If you are going to measure the center point of that ball and the radius at which that balls are rotating, that is denoted by small r. F suffix c is the centrifugal force acting on the ball in Newton, that centrifugal force can be calculated as m omega square r. And finally h is the height of that governor in meters. Now these all quantities are given with their magnitude, that is by means of which we are going to measure, and units are also given for this all parameters. So these units are important. When we are going to measure the height, it should be in meter, whereas when we are going to measure force, it should be in Newton, mass should be in kg, and omega should be in radian per second. Now when we are going to consider the equilibrium condition, that is centrifugal force is acting outward direction, and whereas the tension in that arms are generated, then what we can say that taking movement, because these forces are acting, we can take movement, and we can take this movement at point O. So when we are going to take this movement at point O, what we will get, that centrifugal force multiplied by the perpendicular distance, that perpendicular distance is h, and w, that is weight, is acting, and its perpendicular distance from point O is r. So these are in equilibrium condition. So we can write this f suffix c multiplied by h is equal to w into r, and that will be equal to mgr. Now this w is nothing but m into g. So we can write this centrifugal force f suffix c multiplied by h is equal to mg into r. For this centrifugal force also, we can write that centrifugal force in terms of omega, r, and mass, that is m omega square r, that is the centrifugal force, multiplied by h is equal to mg into r. So m will get cancelled and r will get cancelled. So finally we can get the equation that h is equal to g divided by omega square. When the g is expressed in terms in meter per second square, that's why already I have explained you that units should be there for the given quantities, as we are going to mention this g in meter per second square. That's why h should be in meter, m should be in kg, w should be in Newton. So when we are going to give the unit for this g as meter per second square, omega radian per second, then h is in meter, and if n, that is capital N, is the speed in rpm, this omega can be converted into speed n. So we can write this omega is equal to 2 pi n divided by 60. So we are going to put the value of omega in terms of n, and we are going to get this h is equal to 895. This is a constant which comes because of 9.81 and 2 pi and divided by 60. These are the constants. So these constants will be multiplied and divided as per their position, and we are going to get one constant, that is 895 divided by n square. So here we are going to get the relationship between h and n, where n is the speed of that governor, or directly we can say the speed of engine also. Engine speed and governor speed are the same speed, that we are going to see in some examples. And if there is some changes in that engine speed and governor speed, it will be clearly mentioned in that problem. So we have to take that ratio. Otherwise this n, capital N, which is mentioned, is the directly speed of engine. So this is relationship between h and n. One can observe here that h is inversely proportional to the n. That is, if the n get increase, h will get decrease, and if the n will get decrease, h will get increase. This is relationship for the watt governor only. Now here some notes are there, that is we can observe something. Already I explained you that h is inversely proportional to n square. Therefore at high speed the value of h will be very small. At such speed the change in the value of h corresponding to the small change in speed is insufficient to enable a governor of this type to operate the mechanism, that is to lift the sleeve or down the sleeve. That will be insufficient, that will not be that much sensitive at that speed, high speed, and hence these type of governors are having some limitations. These governors can be used only for very slow speed, that is 60 to 80 rpm, and you know that the engines which were developed or which was there in 18th century or in starting of the 19th century, these engines were having only low speed up to 180 rpm, and for that purpose this type of governors were used. Now this is all for the watt governor. Now watt governor, we have get the final equation as H is equal to 895 divided by n square.